Good morning. Welcome to the video lecture on design of RCC elements. As of now, we have covered about the methodologies, that is the methods involved for the design of RCC elements. Then the limit state method. Under limit state method, we have designed some elements, that is singly reinforced beam, doubly reinforced beam, then one-way slabs and two-way slabs. Now we moved to the third unit, limit state of flexure, limit state of collapse for shear. Okay, and now we will define what is mean by shear, what is mean by shear stress, what is mean by bending. For example, this is a beam having axis in horizontal direction. When it is capturing its load in transverse direction, it will be subjected to bending. This behavior is nothing but flexure. When a member is capturing your transverse load having its own axis in horizontal direction, you may call it as flexural member, right? A member is having a bending moment in different fashion, that is at each and every section the bending moment will get varied. Okay, so due to variation is in this bending moment, the shear stress is being generated all along your section. Wherever you have a difference in bending moment, you will have some shear stress variation. This shear stress variation is caused due to maybe due to the grade of concrete or the interlocking between your concrete elements, the interlocking between your concrete and your steel elements. Okay, let me clarify how the shear is happened in your beams, right? We'll see. This is my beam. This is my beam. This is my support conditions of my beam. RC beam. I am having reinforcement like this. Okay, so this is my neutral axis. This is my neutral axis. This is my center of the beam. When it is getting loading, say W kilonewton per meter. When a beam is getting loading in transverse direction while the axis is in horizontal direction, it will be subjected to some cracks. First thing, when the load carrying capacity is reached, it will be subjected to deflection. So you will be getting cracks in this fashion, right? So you will be getting cracks in this direction. So this distance you can call it as 1. Here 1 is nothing but pure flexural cracks. Pure flexural cracks. Due to the loading, it will be subjected to bending. So the concrete fiber is reaching your ultimate level, so it will be getting cracked over here. This path is nothing but first path. This is called as pure flexural cracks. Then near your support you have a third zone. Here when the load is here, it will be like diagonal cracks. Here also it will be like diagonal cracks. So when you take a small piece of element and you see the cracks is occurred in diagonal fashion. Here also the cracks is occurs in diagonal fashion. This is called as, this pathway number 3 is called as shear predominant area. Shear predominant cracks. These cracks are also called as diagonal web shear cracks. Okay, in between these two regions, the region 1 and region 2, in between you have some cracks penetrating towards the vertical direction, starts propagating from the downward and it is been projecting towards the upward fashion. So this region is nothing but region 2. This region 2 you can call it as flexural shear cracks. Here the predominant failure is due to flexure alone, whereas here the predominant failure is due to flexure and shear. The shear is being accompanied with my flexure. Here the predominant area is shear. Why? Because due to here you have a supporting condition, here you have a loading condition. When the load is being occurred in the beam, it is been pushing off, right? So the cracks will be occurring along your diagonal fascium. That's why it is most of shear area. So shear is nothing but piercing out, it is cutting failure, it is like a brittle failure. So this is the most failure area due to shear. So you need to concentrate your shear part along your edges of your beam. Whereas here you have a flexural failure, along with flexure and shear you will be getting some failure. So this flexure failure is not a problem for my beam. I can accommodate this flexure failure by taking care of the reinforcement and taking care of I can put stirrups over there, and I need to accommodate my shear capacity of my beam. Here I need to arrive a clear idea about my shear so that the shear predominant area should not fail in my beam. Okay, then we will see about mechanism of shear transfer in beam without any shear reinforcement. We have some mechanism over there for my beam so that no need to check for my shear reinforcement. In some way the shear is being transferred to my beam to the supports. Okay, we'll see that this is the support condition. This is my beam where I have given my reinforcement like this. So I'll have tension, so I'll have compression in this area where I have a support reactions of V. So if I give load in this direction, that is in transverse direction, so from the supports it will be like diagonal cracking, diagonal cracks. Okay, when we see the free body diagram for this part, I'll take, this is VD. VD is my double bar force and double force action. Then this is VAX, this is VAU, this side VA. These are some of the forces is being accompanied. When you get diagonal forces, this is the region, that is third region here, and this is the second region accompanied over here. Okay, then what is mean by VD is nothing but double force action, that is the force due to the reinforcement bar which acts as a double force action. Then VAV is nothing but, this is VAV, this is nothing but, that is interface shear. This is the shear predominant, this is the flexure predominant, this is somewhat like interface shear. Then VCZ is nothing but shear resistance of uncracked section. Before the crack occurs in my section, my section is called it as uncracked section. VCZ is my shear resistance of uncracked section. So I can write V is equal to VCZ plus VAY plus VD. This I can VAX and this is VAY. I can write VCZ is my original shear resistance of my member. This is VAY plus VD. So I can calculate the shear in my beam. This is what the mechanism has been transferred. Normally you have a tension in your bar, the compression is being taken care by your concrete. So these are some of the associated elements apart from flexure in your beam. Okay, let me have the codal provisions. Codal provisions, IS 456, page number 72. we need to go through some terminologies related to shear. This is nominal shear stress. Tau V is equal to VU divided by BD. This is the nominal shear stress across my section. This is VU is nothing but shear force due to design loads, that is ultimate load, divided by your breadth of your section. When beams of varying depth, I can go for some section when my beam depth is varying, tau V is equal to VU plus or minus MU by D into tan beta divided by BD. When I have a normal rectangular section of my beam, I can go with this formula to calculate my nominal shear stress when the depth of the beam is varying. Say suppose this is my beam is like this. When my depth is getting varied, I can go with this formula to calculate my shear stress. Okay. Design shear strength. How to check my shear strength and how to design my shear strength. The main thing, one is tau V, another one is tau C, another one is tau C max. This is my tau C. Tau C max is nothing but, you can know from the name itself, tau C max is nothing but permissible shear stress having Newton per mm square. Tau C is nothing but design shear strength of concrete. This is also Newton per mm square. This is my nominal shear stress. So, for a section, you need to check what is tau V value, what is tau C value, and what is tau C max value. Tau V depends upon my amount of the reaction over there with my cross section of my beam. Tau C. How the tau C depends upon? The tau C depends on grade of concrete, say M20, M30 like that. Then second one, percentage of reinforcement, that is PT value. So based on the grade of concrete and the PT value, the design shear strength of the concrete is getting changed. Okay. Then tau C max. This permissible value depends on M20, M30, that is the same FCK. That is the characteristic compressive strength of concrete will be changing. You have a maximum variation of tau C max. It is given in table 20, page number 73 of IS 456 code. It is there in table number 20. This tau C value you can take from table 19 of IS 456. IS 456 code, you can calculate your tau C value, depends upon your grade of concrete, right? Okay. How to provide minimum shear reinforcement? Before that, how to provide shear reinforcement? So, the shear will be occurring in this fashion also, along in this fashion also. So, the vertical shear is mostly predominant, so you need to provide your shear reinforcement. This is my longitudinal bar, so I can provide my shear reinforcement in this fashion. This is my shear reinforcement. Okay. When I see in this pink area is nothing but the shear reinforcement. This is called as shear stirrups. Okay, it will be like this. Okay, this hook, this is called as closed loop stirrups of 135-degree hook. This hook is 135-degree hook, whereas I can provide shear reinforcement in this fashion also. This is called as open loop shear stirrups. I can also provide in this fashion. So it will be like this. This is like this and this is like this. Here I don't bend my shear stirrups bar. So this is closed loop stirrups of 90-degree bend. This bend is 90-degree. Here this bend is 135-degree. This is open loop. This open loop will not contribute much to my beam to take care of my shear. So this open loop I can provide in some unavoidable circumstances. In unavoidable situations, I can go for open loop shear stirrups, whereas the closed loop shear stirrups, this 90-degree, this is not suitable. This is not suitable for seismic conditions. Whereas here, this closed loop, this is too bad. The closed loop shear stirrups of 135-degree hook, this is better for ductility and shear carrying capacity. Okay. Why can't we have only this type of shear stirrups? We have certain another pattern also. This is one-legged. This is called as leg. One leg, two leg. I can put one shear stirrups like this and another shear stirrups like this. So two-legged stirrups. Here, how many legs? 1, 2, 3, 4. So 4 legs. This legs and all, it is purely based on your shear capacity. Okay. Let me now see minimum shear reinforcement. What is your minimum shear reinforcement capability? When tau V is less than tau C, so you can provide. When tau V is less than tau C, the minimum shear reinforcement shall be shear reinforcement can be provided, or else when the tau V exceeds the tau C, tau V exceeds tau C, shear reinforcement to be calculated based on capacity. So this is the criteria. First you need to calculate the nominal shear stress value, then you need to take your tau C value from your code book. So you need to check whether this is less than tau V or greater than tau V. When tau V is less than tau C, you need to provide minimum shear reinforcement, or else in some cases no need to provide shear reinforcement also, it is being barred by your section. Okay. When tau V is greater than tau C, must to provide shear reinforcement based on your capacity of your shear capacity of your section. Okay. These two we need to check with tau C max. When tau V is greater than tau C max, redesign your section for shear along the depth of the section. Okay, these are the criteria you need to check whether your shear capacity is okay or you need to provide. In some cases, if you provide shear reinforcement, two-legged stirrups may not be sufficient to take care of my shear. That's why you can go for another leg also, so that you can accommodate your shear value. If not, you can go for another legs also. This is 2-leg, you can go for this is 3-legged or 4-legged or 5-leg. It is based on your section capacity what you have designed for your member, right? Or else first is increase the first criteria, increase the legs. This is the first thing. Second thing, increase the dia of bar. Then third thing, if the increase of leg is not sufficient, increase of dia of bar are also not sufficient, you can go for redesign the beam depth. So this is the only criteria to take care of your shear. For example, in general, I can tell you this is my cross-sectional element. If you give load, it will be like a punching action in your element. So you will get some failure along this support conditions also. This punching effect will be predominant, so that your member is getting failed as brittle failure. This is called as brittle failure. To avoid this brittle failure, if you need to provide shear reinforcement, it is okay. If the shear reinforcement is not able to accommodate your section for your loading, you can increase your thickness of your member. For the same load, I am increasing my thickness so that your depth will be safe under shear. This is the common criteria generally we need to follow for your section. Okay. Then factors affecting shear. The main factor is FCK, that is your grade of concrete, then PT, percentage of tensile steel, third one PC, compression steel, then fourth one shear span. So these are the main criteria you need to check. These are some of the factors which has been affecting, because FCK and PT will correlate under tau C value, then tau C max value also. So based on these values you need to take care of your shear. So these are some of the factors which are mainly affecting your shear behavior of your element. Okay. Then in next class we will see about some problems associated with shear also. Okay. Let me conclude this lecture. As of now, we have seen what is mean by shear, what are the types of failures occurred in my beam due to shear. We have three types of shears. One is flexural shear, then one is web shear, then one is splitting or diagonal compression shear. So we have bending moment associated with my shear also. So shear, it is a predominant only for the support region. It is mostly okay for my flexural shear cracks. Okay. As of now, we have seen some general terminologies, how to provide the shear reinforcement and when to provide my shear reinforcement. Then some of the checks related to my IAS codal provisions. Then what is mean by shear stirrups, what is mean by legs and all we have seen now. In next lecture, we will see about the design of beam for shear. Okay, thank you.